So how did we get to being able to measure the metabolome as we know it today? The first thing was the metabolome is very, very complex. And the more sensitively we can examine, the more we see. And so the first thing you have to worry about is, can you separate the members of the metabolome out such that you can look at them in more detail? And I mentioned Tony James and A.J.P. Martin. Martin went on to get the Nobel Prize for partition chromatography in 1952. He had laid out with Martin Singh a paper in 1941, all that, during the war, when everybody else was worrying about fighting. They laid out a premise for how things could be separated in a two-phase system. And because of that, a guy called Goulet, who had nothing to do with separation science, got in to look at this. I think he was more a physicist and an engineer, and figured out that the right direction to go with gas liquid chromatography was in the direction of doing capillary GC, where you don't have any packing on the inside of the tube, the glass tube that we use. And so this is the difference, is an example of the difference that you see. But on the lower picture here, the separation was on a 3 meter, or I think it's a 3 foot by 1/4 inch diameter glass column. These are 5 barbiturates that are separated, 1, 2, 3, 4, and 5. And you can see that they're just about separated, but not well. On the other hand, when you put the same mixture in a capillary column, this is now a 10-meter column, and the width of the capillary is 0.5 millimeter. And why you can go to a much longer column is now you don't have packing. If you had packing in there, then the pressure required to push things through the column would be so high that you would actually lose more than you gained by going to longer columns. But getting rid of the packing allowed things to go to much longer columns. When I first started using I didn't hear that one properly. Okay, so let me continue. So the first column that I was able to use was 100 meters long, and it was made in borosilicate glass, and one had to straighten it out, and it was quite difficult to do. So I had many adventures in that early stage. Later, liquid chromatography was introduced by Horvath and others in the mid-60s, and that is now developed as far as HPLC or UPLC by the Waters Corporation. So in this picture, you'll see the same separation, but done with different particle sizes. So when the early forms of HPLC used 5 micron sample size and a 50 millimeter column, and it took 10 minutes to do the separation. Then it was reduced to 3.5 micron, and the column size could be reduced by 50%. And this allowed the use of shorter columns, and now the same separation could be done in 4 minutes. And then gradually we went down to 2.5 and finally to 1.7 micron. And now the column size is now 3 times smaller than what we started with. And this now allows the same separation to be run in 1.1 minutes. So it's really improved the speed at which we could do things. So we've used this principle for our metabolomics, whereas we were started off using 30-minute separations, we're now down to 6-minute separations for very complex mixtures. There is a finite limit to all of this because the back pressure goes up quite quickly with the decrease in particle size. So I suspect that we will eventually get to an open tubular column for HPLC. Okay, then the next stage was how to connect the GLC or the HPLC to the mass spectrometer. Now, the mass spectrometer works at extremely high vacuum or low vacuum, depending how you look at it. The vacuum inside the mass spectrometer is better than that in outer space. And we need that because we want the ions that we're going to measure to move freely without interference of running into other molecules. And we want to move them in electrical fields so that we can measure what they are and how much they weigh. Reihager, for the Swedish group, developed a GC interface, but I think the really important one that was developed by John Fenn has changed everything for everybody. And that was the development of the electrospray ionization interface. And we see that here. It seemed impossible prior to this point that you could go from a liquid that was going to enter the mass spec, because when water evaporates, it produces 500 times the volume of the water in the first place. So how on earth could we do this and do it well? And Fenn was not a mass spectrometrist. He was interested in ion beams. And the way this works is the fluid that is coming out of the column goes through a narrow orifice, and there is an electrical charge difference between the tip of the orifice and the front of the mass spectrometer. When you spray fluids through a narrow orifice, you generate a spray. Some of you may have tried this or done this. If you take a bottle, a squeezy bottle, and squeeze it on your face, you will feel that the fluid that hits your face is cold. And this is the key. So what was happening was the droplets that you see here that are coming out of this orifice have the charged materials in it, and they're in a relatively large droplet. But if you have a gas coming in the opposite direction, these droplets become smaller and smaller. But inside the droplet, the coulombic pressure, because positive charges don't like to be with positive charges, so there's an outward force in the droplet of the material, the charged material within it. And so eventually that force is so large, it breaks the droplet completely open, and the compound goes into the gas phase. So here you are, a protein, an intact protein can be turned into a volatile protein without heating it at all, and do so at atmospheric pressure. It didn't seem possible. And of course, Fenn got the Nobel Prize for this in 2002. Now, it can be applied to anything that's coming out of that column. So not just proteins, but peptides, as people quickly found out, complex lipids, metabolites of all kind. And so that's what we now use in metabolomics to look at the compounds that are present and that we have separated. I mentioned NMR before, nuclear magnetic resonance. It's a wonderful technique. It's not sufficiently sensitive, but it has great virtues, one of which is it's a spectroscopy, and therefore you can get the spectrum without destroying what you're measuring, unlike mass spectrometry. It had definite development stages, one of which was to use superconducting magnets. The early work in NMR was done with fixed iron magnets. They were huge. You had to have in the floor, you had to put a lot of support in to stop the magnet dropping through the ceiling into the floor below. And so that was getting superconducting magnets, which were much lighter, but gave a much greater magnetic field, was a huge development. And it came to me to be exposed to that in the late 1970s and early 1980s. Also, Fourier transform as a grad student was brought to be by the development work by Ernst. And then, as I'll show in just a minute, Ed Bax managed to develop two-dimensional pulse sequences that allowed us to look at individual compounds and look at their NMR spectrum much more quickly than hitherto. So this is from a paper that I published with Mike Geckel in 1982. And prior to that, we had been measuring the bile acid derivatives in an ion magnet. And all we could see was the methyl groups and the protons that were epimeric to the hydroxyl groups. The rest was just called the steroid hump. And so Mike invited me one day. He said, "Why don't you bring your sample up and we'll put it in the new instrument that we just brought in and see what we get." And the picture we got was the one here at the bottom. And what was the hump clearly was not a hump anymore. It was actually a series of little humps. A very simple methodology was used to look at the tumbling rate of the molecules. So we were able to look at the methine, that's the CH part of a molecule, and the methylene, the CH2, and by just changing the timing of when we acquired the spectrum, these two components could be separated out. It allowed us then, bit by bit, it took 8 months of work to actually lay out the entire proton spectrum of a bile acid. And it was the first time anyone had done that for a molecule of that complexity. So as I said, 8 months of work and many, many hours at night working on this. Well, a chemistry student came to my attention back 3 years later, and Vince Waterhouse, and he had read about Ed Bax's work. And this is an example of what we got. This is two-dimensional NMR, and it takes advantage of the fact that the carbon-13 spectrum was well known and quite well separated, as you can see here. And by putting a saturating pulse at the same wavelength as each of these atoms, you could now find out what proton it was connected to. This was called a het core experiment, and that was published in the Journal of Lipid Research in 1985. And I have to say, it's the only manuscript I've ever submitted that was accepted without changing a word. It happens very, very rarely. The good thing about it was, instead of taking 8 months, this took 24 hours. We got the computer to run the experiment for about 21 hours. We then did some workup to generate pictures, and then about 15 minutes of discussion. And so we were able to look at multiple bile acids, and that was the basis of this particular paper. Okay, so I'm going to concentrate on LC-MS data and take a look at what we get in a metabolomics experiment. So this is what we call a total ion chromatogram. It's the summation of all the ions, all the metabolites that were being eluted as they came off a column. The column was what we call a reverse phase column. In other words, it's sticky for things that are hydrophobic. So things that are hydrophilic will come off very quickly. So these are over here, these are the hydrophilic compounds. And we can see what their mass is. They're printed out above this. This particular one is actually the oxidized form of glutathione. And glutathione is one of those things that all of us have to have in every tissue. It soaks up free radicals and any of those that are being generated. So it's sitting in the background looking after us all the time. But there are many other compounds, and some of them are intense and some of them are weak. We elute them by applying a gradient, a linear gradient of acetonitrile. So acetonitrile is a hydrophobic liquid. It's miscible with water. And so we can raise it from 0 at the beginning of this chromatogram and take it all the way up to 100%, which occurs over here. And then we have a wash period, and then the sample recycles to go back to the start. Now, if we know what we want to study, we can put in a value. Hold on, yeah, so it's collected everything. So we can then not only go back and look at what the individual components are, but we can also do MSMS, which breaks each of the compounds down, so we get a molecular fingerprint. So this is what we would see if we then said, okay, let's make a selected ion chromatogram. And it's for the amino acid phenylalanine. Phenylalanine has a known empirical formula. And so we can calculate, because we know the masses of carbon, hydrogen, nitrogen, and oxygen, we can come up with the molecular weight of phenylalanine. And in this case, what we've done is we've taken one proton off the phenylalanine to make an ion, because that's what we're going to measure. So instead of having a mass of 165, it has a mass of 164.072. And if you look very carefully back up here, you see that this small peak here is 164.0719. In other words, that's the phenylalanine peak amongst all these others here. Now, we can also do metabolites in experiments by doing it in a targeted way. So if we didn't know what we were going to find, we could do an untargeted method. But if we knew from some other experiments, and it could be a transcriptome experiments or a paper we read in the literature, we might want to look at a specific group of compounds. And in that case, we do targeted metabolomics analyses. So if we know what we want to measure, we also know what the mass of that particular compound will be as an ion. So we can filter those so that when they come through the interface into the mass spectrometer, we can say, okay, filter out, let's only have ions of this mass to go through. And then we can fragment them by accelerating the ions and running them into a little puff of gas, and it causes the ions, the ion of the compound to get hot, and it now breaks in a reproducible way. And this becomes a mass transition. So one side of the mass spectrometer is filtering for the molecular mass, and the other side of the mass spectrometer is measuring the product ion of this combination. And it's usually very unique for each metabolite. So we do this. So we do this for about 10 milliseconds of time, typically, and then repeat it for each individual compound. And when we're done, we come back and repeat this whole series of measurements. And this is a reconstruction picture that you see here. In the item above, you've got the short chain fatty acids from acetate, propionate, isobutyrate, butyrate, and so on and so forth. And then down here, we have the Krebs cycle intermediates that include malate, 2-hydroxyglutarate, succinate, fumarate, isocitrate, citrate, and so on and so forth. And so by putting in standards, we can calibrate what we're getting here and come out with quantitative numbers. And that ultimately is the best way to be. When you're doing untargeted work, you're usually comparing things, and therefore the difference in areas under the peak is a relative term. Okay, so now we've collected the metabolomics data. How can we turn it into a a form that we can use for understanding what is going on in the system that we were exploring. The mass spectrometers are, the data is recorded by the manufacturers in coded forms, and this is done because many of the applications of this involve exploration of new pharmaceuticals, and therefore they can't have people changing the nature of the data. So each manufacturer has their own coded form. So normally this would require you using the manufacturer's software to be able to read and interpret the data. This becomes a problem when you have multiple groups interested in using the data, because each version of the software has to be bought independently, and they can be a lot of money. $30,000, $40,000 is not unusual for the software from the manufacturer. So it's good to be able to get freeware, and most of us are using freeware. And so there are many can be used to decode and then analyze the data. The one I started using at the beginning was ESI-MS. It was generated by Gary Swiesak's group at Scripps. It eventually turned into a commercial form. So we switched in, I think, in 2015 to MZmine, which is currently 4.537. It runs in the background on a PC, Linux, and Mac operating system. And we also moved to MS Style. There are multiple versions of this. It was developed as a collaboration between Hiroshi Tusagawa in Japan and Oliver Fien at UC Davis. It's currently in a high version in the 5s, but our preferred version is 4.9. It has a GUI, a graphical user interface, which we really love, but that's only available for the PC version of the equipment. One of the people who I work with in the workshop that NIH funded is Zhu Shadu, and she has recently developed a program based on MZmine called ADAP-Big, and that's also available, and it runs on both Windows and Macs. And then I'm very excited to be able to be taking part in analyzing ASARI. It's a new program, runs on Mac and Windows operating systems, particularly good on Mac. It's very easy to work on a Mac. And it was developed by Xuxiao Li, who also took part in the workshop that I ran for NIH. And he and Joshua Mitchell and I have been working. I'm a tester, and they are the generators. But the beauty of it is that it runs really, really fast. So I had a pretty big data set to analyze, which I was using through MS Style. It had 824 samples to be analyzed, and it on my Mac with, I think, 16 gigs of internal memory and a terabyte of SSD, it took 2.5 days to process the data. On ASARI, doing that same data set, it took 10 minutes. Huge difference. It's still being developed, and I'm not using it as my regular way of doing it, but I think that's a high prospect in the future. So how do we annotate? So you saw before that we can get these total ion chromatograms, and by going in, we can look at the individual ion feature. So an ion feature is something that comes out at the same retention time within a few seconds and has the same mass within a couple of millidaltons. And so this is seen across all the data sets. But just having those pieces of information is not enough. And so we perform the fragmentation of the peptides, of the metabolites that we can measure. And these go into different databases. They can be a public database. They can be an in-house database. that you develop, or they could be to proprietary databases, which are usually expensive. So if you go to the MS Style GitHub website, there are downloadable community data ion data MSMS databases, both for negative ions and positive ions. They very nicely integrate with MS Style, allowing for direct annotation, and I'll show that in a minute. The limitations of it is that the database was not generated in one lab or with a standard method. It came from investigators using different chromatography, different mass spec instruments, different conditions for making the MSMS spectra, and different biases according to the type of work that they wanted to do. There are commercial metabolite standard kits where the metabolites can now be run on your machine under exactly the same conditions as the samples. And so this gives you an extra degree of assurance. So you get retention time, you get the correct mass, and you get the correct mass fingerprint. The limitation is that the metabolite range is much bigger than what's in the standard kit. So there are advantages and disadvantages of it. If you're looking doing metabolomics on a patient, if you use a purely intermediate metabolite standards library, you don't see what the drugs are that the patient is taking. And this can be important from an ethical standpoint. Okay, so how do we go about doing the analysis of these data? So first of all, we take the raw data from the mass spectrometer that's been collected by the mass spectrometer. We analyze it with one of the software programs that I described. So now we have exported from each of these programs, usually an Excel sheet with a list of the ion features, some of which are annotated, and many are not, as it turns out. That's another topic. So we have now material in these Excel data sheets. Sometimes there are contained in the sample or the data sheets you get, there are contaminants. And what I mean by contaminants, these are compounds that have nothing to do with the biology. They came from the sample processing. They came from the tube that you put the specimen into when you transported it to the lab. And then there are all sorts of other contaminants, people's sticky fingers, and even the solvents that we use to run our mass spec contain contaminants. So they're easily recognizable because they usually are the same in every sample you measure. And so you can go through what you've got and filter them out before you go to statistics. The best package that we use, and it's essentially free, is MetaboAnalyst. It was developed by David Wishart's group, and it's now continuing to be developed by Dr. Lee who's in where is he in Canada? He's in Montreal in Canada. Yeah. And so it provides both univariate and multivariate statistics, hierarchical clustering, machine learning, and pathway analysis. And it does all this for free. It did have an option at the end where it would produce an integrated report output, but now that's you have to register. It's maybe $700 to $1,200 a year to freely use the service, and now you get everything. But you can download all the pieces of data that were run during your time on the software site, so you can reconstruct the data for presentation very easily. So it's not a real handicap, but it's really nice to have the output, because if you're working with somebody who is not connected to the lab, you can send them a report, and it's very, very easy to just send it And there's a lot of background information given in the report that can be helpful to the person receiving the data.